So the notes that we're doing today, we're going to determine whether a linear or quadratic model best fits the data. And we've learned how to do linear regression as well as quadratic regression. So now we're going to give you data and say, okay, which model is going to best fit the data without telling you which one is the answer. In order to do that, we're going to have to talk about two things. One is the correlation coefficient. And what the correlation coefficient is designated as the letter R. Okay, and it measures the strength and direction of a linear relationship between two variables. It really just tells you kind of how they're related or if they're related. So a positive correlation is as one variable increases, so does the other, and vice versa, meaning as one variable decreases, the other decreases. An example of that would be the hours you study versus your grade. Typically, the more hours you study, the more of the hours you have, the higher your grade would be. So as one thing goes up, the other thing goes up. Let me get my pens ready. So as one variable goes up, so does the other. All right. Now, a negative correlation doesn't mean bad. It just means as one variable goes up, the other one goes down. So an example of that would be like the number of absences you have. The more absences you have, the lower your grade typically is. All right. So those are just examples of positive and negative correlation. All right. And when we do our scatter plots, you're going to be able to see positive correlations by them like going up and up together, and negative correlations on a scatter plot would kind of be looking like this, because positive, as one thing goes up, so does the other. On a negative correlation, as like the independent variable gets bigger, the dependent gets smaller, or vice versa. Now, we can use correlation coefficients for linear data, but when we're using quadratic data, we're going to have to kind of look at something called the R squared. And the R squared is the coefficient of determination. Okay? It is a measure that allows us to determine how certain one can be in making predictions from a model or graph. So we're trying to figure out how certain we can be that our model is actually a good predictor. The coefficient of determination is such that 0 is less than or equal to R squared is less than or equal to 1. That denotes the strength of the linear association between x and y. So our R squareds, the lowest it can be is 0, the highest it can be is 1. And the closer the R squared is to 1, the better the model. So we're going to look at our R squareds and see whichever one is better than 1, and that typically is going to tell us which model is best. Now, you guys need to get R squared on your calculator. So to do that, you need to go to second and the number 0, and you're going to see that that's your catalog. I need to scroll down to diagnostic on. So keep scrolling down all the way to the D's, go all the way to diagnostic on, and once you get there, press enter. Then on your main screen, you should see the diagnostic on word. Press enter again, and you should see the word done. And now you've put into your calculator, you've told your calculator, hey, besides just doing linear and quadratic regression, I also want to be able to see my R and my R squared. So with your graphing calculator, let's do letter A, the falling object example. It says a stone is dropped from a high bridge into the water. A camera takes a photograph every 0.4 seconds showing how far the stone has fallen. The distances are given in the table for the first 2 full seconds. So we have time elapsed versus distance fallen, right? Okay. So my independent variable is going to be the one that doesn't change, and my dependent one is going to be the one that does change. So my distance fallen is going to depend your distance fallen is going to depend on the time elapsed. So I'm going to make x my independent variable and y, either way, my dependent variable. All right. So when I go to find the linear model, I'm going to do what I've done on my calculator, where I'm doing stat edit, and go ahead and go to stat edit and enter in your data. Your L1s should be your x values or your independent values, so 0, 0.4, 0.8, 1.2, 1.6, and 2. And then your distance fallen is going to be your y values or your L2 values. So you want to go to stat edit and enter in all that data. Do you need your quiz?
Oh no, I was just dropping it.
Okay. So let's go ahead and do the linear model. I'm going to go to stat edit. If there's any data, if you remember, go to the very top on your L1 and press clear and enter. So go to the L2 and L1, press clear and enter. In my L1s, I'm putting my independent data or my x's. So I'm putting 0, 0.4, 0.8, 1.2, 1.6, and 2. All right. In my L2s, I'm putting in 0, 0.78, 3.14, 7.04, 12.56, and 19.6. All right. And I don't know if you can hear with all the commotion of the locker rooms, but so I'm in stat edit, and again, you're typing these in as I'm saying them out loud in your calculator under your stat edit, under your L1s and your L2s. 19.6. Okay. Now, once you go to stat edit, I'm going to do my linear model first. So if you remember how to do that, just go stat. So my second step is I'm going to do stat, calculate, and for number 1, since I want to do the linear regression, I'm going to press number 4 or go to number 4 where it says linear regression. Okay, so it says like L-I-N-R-E-G AX plus B. Now press enter, and on your main screen, if you remember, I still want you guys to add in, once you press enter on this, you're going to have to enter your L1, L2, Y1. And depending on your calculator, you either type in like second 1, which would give you L1, second the number 2, which is L2. And then to get the Y1, you do vars, Y-vars, number 1 for function, and number 1 for Y1, and press enter. And what's going to happen is you're going to come up with a linear model, and you can just estimate these to 2 decimal places is fine. So I'm going to make my linear model, y equals, and this is what's on my calculator. My a value or my slope is going to be 9.8, let's just say 9.8x plus, and actually if I look closer, my b value, excuse me, my y-intercept is actually a negative, so I'm going to say 9.8x minus 2.62. Right? And my r squared should be on my graph, so, or excuse me, on my calculator. If I look at my r squared, it's going to be 0.9212, let's say 98. Put it out a couple decimal places. All right, so I've just determined the linear model and the r squared, and the r squared is pretty good. It's close to 1, but it's 0.92, so we're going to have to see if the quadratic model is better. To do that, I'm going to go to step 3. I'm going to do stat calculate, so go back to stat, press the stat button, calculate, but now go to number 5, because number 5 is the quadratic regression. So that, now I'm going to determine the quadratic model. So do quadratic regression and enter. All right, and again, what I should say really quickly, sorry, is when you go to do quadratic regression, now I want you guys to do L1, L2, Y2. We're going to put the quadratic model in our Y2. All right, so our Y1 will be the linear model, our Y2 will be the quadratic model. So when we graph it, we'll be able to see both models or pick the one we want. So again, stat calc, go to quadratic regression, L1, L2, vars, y-vars, function, but scroll down to Y2. Once you press enter, we're going to come up with our answer. Well, our quadratic model is going to be y equals 4.9x minus 0.005, sorry, 4.9x squared minus 0.005x. Now be really careful. If you look on your calculator, it's negative 7.14, but that says e to the negative 4. That means I need to move over 3 decimal places. So be careful there that this is what I think your calculator should look like, 142, and if you keep looking, you'll see e to the negative 4. That is actually not negative 7 point, okay? What it is I'm going to take this right here, 7142. If I move this over 4 places, 1, 2, 3, 4, your c value is actually going to be 0.0007142. So just be careful that the calculator obviously is telling me great things, but I've got to be careful that I actually look at the data and solve it in the sense that when my answer came up, I've got to be careful that this is actually 0.0074142. Now my r squared for my quadratic is 0.9999. So right away, when it says which model is better, I know the quadratic model is going to be better, and the reason why is because my r squared is closer to 1. So I'm going to put for which model is better, I'm going to put quadratic, I'm going to put r squared is closer to 1. Now we're going to talk about it in class, but if you guys could go to your window and make your x minimum 0, okay, and your x maximum 2, and then let's go to your y's and make your minimum 0 and your maximum, let's say 20. If you press graph, you should be able to see the linear model and the quadratic model. All right. We're also going to make sure that when we do this, that if you put your data on, I'll be able to tell which graph is better. So you need to make sure your stat plot is on if you don't see the dots. If you do, your graph's going to look something like this. You're going to have scatter plot dots kind of here. You'll see the quadratic data the quadratic model, and then you'll see I'll kind of do in blue the linear model. So you can also tell by looking at your graph, and we'll review this in class, that if the scatter plot looks like the quadratic model or the parabola goes through more data points and is more accurate, then it's going to be the quadratic model that's best fit versus the linear model. Now, whatever's closer to 1 is algebraically more accurate, so it's easier to say that r squared is closer to 1, but no, you can also use your graph. Okay, then it says use your model or your graph to predict how far the stone will have fallen after 3 seconds. Well, once you pick your model, so if I'm doing this quadratic model, if I want to find out how far after 3 seconds, well, 3 seconds is really my x. So there's 2 ways of doing this, okay? You can take your equation above, and I can put a 3 in for every place I see an x. Okay, so I'm going to plug in 3. So I'm going to do that kind of my calculator setup and say, oops, hold on, stat. Yeah, I'm going to say, 4.9 times 3 squared, and then minus 0.005 times 3. So I'm just plugging in a 3 every place I see an x, plus 0.000742. Okay, and I'm going to get an answer of 44.09. All right, and that would be how far the stone will have fallen. That's how many meters it was fallen. Now, if you guys remember how to predict on the calculator, you also could do second trace. Okay, so this is from plugging in. You also could do second trace, and then number 1, which is value. And when it says x equals, just plug in x is 3. All right, and since x is 3, if it says invalid dimensions, I just have to make my window bigger. So I'm going to go to my window and make my window maximum 3. So that way when I do second trace value,
And there were leaves covering the skull, and I kind of like fell face first in the hole. So yeah,
I get, when I plug in 3. Now,
really like it hurt.
I looked at my answer and I got 26.79, but I realized I still have 2 of my models on my graph. So if you are going to do it by using the calculator, which for a lot of you it's going to be much easier just to plug in, so we'll probably just stay with that method, I need to go back and clear out the linear model. Since the quadratic model is better, I can only put the quadratic model on my graphing calculator. Then I need to do second trace value x is 3. And I get 44.11. So on the calculator, I got 44.11. By hand, I got 44.89. So that's a great estimate. So I would really prefer you guys to just take your model and plug in. All right. So the same thing when the bridge is 100 meters above the water, how long will it take for the stone to hit the water? Well, 100 meters is going to be my distance, and distance is my y. So I'm going to take the equation that I want to use, which is my quadratic. Now, if you look, when I go to plug this in, the bad part is I've got a squared term and an x term. So for this, it's going to be much easier, believe it or not, to use my calculator. Because if I move minus 100 over, I'm going to have to factor this, but I'm not going to be able to factor this. And I'd have to use quadratic formula. So we really indeed need to use our calculator for this. So when we go to my calculator, I need to make sure that I only have my y2, right? You deleted your y1 because my y2 is my quadratic model. Right? So once you have that, press graph. Now, if you remember, I'm going to go to my y3. Because my y is 100, I'm going to go to my y3 and put in 100. And I'm going to see where that line intersects my graph. All right? If I can't see it, I need to go back up to my window. Well, since I'm doing y is 100, I'm going to need to make my maximum like 150. So I'm going to graph. I'm going to put y is 100. And see where it intersects. If I still can't see it, I'm going to have to continue to change my window until I can find out the intersection of those 2 points. So what I'm looking at on my graph after changing my window is my parabola and then where it intersects. So I'm going to do second trace intersect, press enter 3 times, and my answer is 4.52. So it would be 4.52 seconds. All right, so we're going to use our calculator to help us figure out much more readily with quadratics than we are with linear equations, because we're going to be able to more readily find the answer when we can use our calculator. All right, if you look at letter B, we have a basketball. All right, I'm going to go ahead and do stat edit, and let's go ahead and enter this data into our calculator. So I'm going to put in 0, 0.1, 0.2, 0.3, 0.4, and 0.5 into my graphing calculator under stat edit. So again, I'm going to stat edit. Okay, my L1 is my time in seconds, my L2 is my height, because the height depends on the time. All right, so in L1 again, you put in 0, 0.1, 0.2, 0.3, 0.4, and 0.5. Then in my L2, I'm putting 4, 4.9, 5.6, 7.2, 5.8, and 4.1. I'm going to do stat calculate the linear model. Just make sure you do L1, comma L2, comma vars, y vars 1, and enter. And when I come up with a linear model, I'm going to get, for like 2 decimal places, 1.37x plus 4.92, and my r squared is 0.0455. All right, let's go ahead and find the quadratic model. So I'm going to do stat calc, but now I do number 5. Then when I do, so this is stat calc number 4, this is stat calc number 5. Again, make sure with quadratic regression, put L1, comma L2, but then put in your Y2. So I'm going to put my quadratic model in my Y2, my linear model in my Y1. When I go to do vars, Y vars, instead of typing in Y1, you're going to put Y2. Come up with your quadratic model, which would be y equals negative 38.21 x squared plus 20.48x plus 3.65, and my r squared is 0.799. Well, which model is better? My quadratic model is going to be better, and it's going to be because my r squared is closer to 1. All right. If I want to look at this data and be able to predict, I'm going to have to go to my window and change my window. I'm going to go to my, look at my data table, and it looks like if I do my window, let's make our x minimum values 0, and let's make our x maximum, it's only to 0.5, so let's just go to 5. I'll make my y minimum 0 and my y maximum, I don't know, let's say 15, and see if that will work. So I'm going to my window and I'm changing my window 0, 5, 1, 0, 15, 1. I'm going to press graph, and I should see my scatter plot as well as the linear and the quadratic data. And if you look, it kind of looks like this. They're both pretty bad models. 0.04, that's terrible. 0.799, that's closer to 1. But if you look, your data kind of looks like this, right? So your data looks like this. But if you look, your quadratic model does something like this. I'm going to do it in red. And then my linear model looks like this. So they're both pretty poor models, but the quadratic is going to be better. So I'm going to go back to my Y1 and clear out my Y1 just so I have the quadratic model listed. I only want the Y2 listed. Okay. Then it says, what's the initial height of the ball? Well, the initial height would be when my Y value, okay, I want to find my Y value, sorry, when I'm initially starting. So when I originally start, which would be time is 0 seconds, that would be when x equals 0. What I want you to do is go second trace, number 1 for value. And when I do second trace value, number 1, plug in x as 1 and see what you get. Now, it says that it's negative 14.08. Obviously, that can't be realistic. So if I have a negative when I'm doing initial height, right, we've got to say, hey, what does that really mean? Where is the ball really? Well, the ball really isn't in the negatives, okay? The ball is really on the ground. So some of these predictions we're going to have to make sure make sense, and we're going to have to make light of them and figure out what they are. All right, number 5, use your model, predict the height when the ball, when 1 second passes. So now I want to know when x is equal to 1. So go back to second trace value. If I type in x is 1, I get negative, did I do that right? Negative 14 point, hold on. Clear that. 30.8. Let's graph. Okay, second trace value of x is 1. Second trace value, x is 0. Okay, sorry, 0, why did I put 1 in there? Oh my gosh, I'm going to go back. 0. When I plugged in 0, I'm bad, I don't know what I just did. When my time is equal to 0, I get 3.65 feet. Okay. So 3.65 feet is where I am at the initial height of the ball. Now, if I do x is 1, sorry, now if I do second trace value of 1, I'm going to get the negative 14.08. Well, that doesn't make any sense because the ball can't be in a negative. But the ball, what's going to happen is because I only went, if you look, it only took 0.5 seconds for it to land. My ball is going from here to here. After 1 second, it's going to go in the negatives. It really just means the ball is on the ground. All right. The last two, how many seconds have passed when the ball is 6 feet in the air? Well, if I look at 6 feet, 6 feet is going to be my y. So I'm going to go to y equals and plug in 6. I'm going to go to y3, and I'm going to find the intersection of y3 being equal to 6 with the other points. Now, if you look, your graph's going to look something like this. Here's my parabola, and then here's my graph. And if you look, it's actually going to intersect at 2 places. All right, the reason why it's going to intersect at 2 places is because I'm a parabola. So I need to find this intersection point and this intersection point. And the way you do that is second trace intersect. All right, now you need to have to find the first curve, second curve, and so on. So you need to take your cursor, go over to those places, and press enter, enter, enter. And it should come up with a guess, and one of my intersection points is 0.36, 9,6. But I also have another point that if I do second trace intersect and I go to the other point, I'm going to get an intersection of 0.116. Oops. So my other point would be 0.166,6. And the reason why there's more than one answer is because you have a parabola. Whenever you have quadratics, we're going to have to be careful that sometimes when we have a y determination, we're going to have to find out the intersection of those 2 points.